by just saying, that if you have any questions, please feel free to interrupt at any time. I hope I tried really hard to make this talk friendly and not too technical. So we'll see how it goes. But again, please feel free to stop me at any time. Okay. So throughout this talk, M is going to denote a 3-manifold. So M is a 3-manifold. And I'm going to use gamma to denote its fundamental group. Okay, so that will be the notation for this talk. All right, so I first want to start with the geometrization theorem. So I think most of us know this great theorem, geometrization theorem, and it was first conjectured by Thurston in the 80s, and he proved it in some cases. But then it was fully resolved by Perelman, famously in 2003. So let me say that. And what the geometrization theorem says is that if you take any compact irreducible 3-manifold, so let me say this here, every compact irreducible 3-manifold can be canonically decomposed or canonically, let me say actually, canonically cut along tori in such a way that the remaining pieces uniquely admit a geometric structure. Okay, and we know, a finite volume, and we know that this geometric structure is modeled on one of 8 possibilities. So let me say it like this, a geometric structure modeled on these 8 possibilities. So there is Euclidean, Euclidean 3-space, spherical 3-space, there's hyperbolic 3-space. There's some product geometries you could have, like H2 cross R, S2 cross R. You can have nil, that stands for nilpotent, sol, that stands for solvable. Sometimes people write solve. And there is the universal cover of SL2R. Okay, there should be 8 of them, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's 8 of them. And in many ways, we can say that hyperbolic geometry is sort of the most interesting, but I'll give a little hint as to one reason why we might say that. And here is sort of a corollary of this theorem, which we call hyperbolization. So it's true that if M is compact, irreducible, and atoroidal, then actually M is hyperbolic. So M is hyperbolic if and only if the fundamental group of M is infinite. Okay, so we can think of hyperbolic manifolds, or I guess after you do this geometric decomposition, your piece is going to be hyperbolic if and only if it has this large fundamental group, and large in the sense that it's infinite. So hyperbolic 3-manifolds have very interesting fundamental group. Okay, so if M is hyperbolic, let me say this here, that means that we can realize M as a quotient of hyperbolic 3-space by isometries. So here gamma acts by isometries on H3. So in particular, if we think about the isometry group of H3, we can realize it as the matrix group SO31 with real coefficients. And you should note that sometimes you think of this group as being basically PSL2R, PSL2C. Well, this is really up to index 2. So here, these ones are actually the orientation preserving isometries, which we usually denote like this. Okay. All right. So this is just a hint as to why hyperbolic sphere manifolds are pretty interesting. But here's another reason why they're really interesting. And here's the following rigidity theorem of Mosto and Prasad. So this is called Mosto and Prasad rigidity. And I'll just mention here that Mosto proved it for the closed case. And this is around 1968. So it's pretty classical by now. And Prasad generalized it to the full finite volume case a little bit later. So I'll say that. So it was sort of first shown in the closed case, and you needed a lot of extra work to also show it in this bigger generality. Okay, so Mosto and Prasad rigidity, what it says is that if you are given a hyperbolic free manifold, or if you're given two of them, so let's say you have M1, again, we realize it as this quotient, and M2. And these are now two hyperbolic three manifolds of finite volume. Finite volume. Then the following is true. Then it turns out that we can say M1 and M2 are homeomorphic. If and only if they're isometric. Which is true if and only if their fundamental groups are isomorphic. So what's great about this theorem is that you notice here we have that these two manifolds are homeomorphic. So in particular, it means that they're equivalent in terms of topology. But that's only true whenever they're isometric. So again, that means that they're equivalent in terms of geometry, which is also true if and only if their fundamental groups are isomorphic. So they're equivalent in terms of group theory. So this is great because it means that it allows us to study hyperbolic free manifolds from any one of these three different points of view, because each one of these determines the other two. So that's quite interesting about hyperbolic free manifolds. And you probably know that this actually holds more generally for hyperbolic manifolds of dimension at least 3, definitely not true in dimension 2. Okay. All right, so the title of this talk was Virtual Properties of Three Manifolds. I've already given you a very quick introduction to three manifolds and why we should care about the ones which are hyperbolic. So let me just remind you what a virtual property is. So virtual properties. So we say that M, so this is the three manifold M, is virtually some property. So let me say like this, some property. If there is some finite cover, let's say M prime covering M, which, or let's say such that M prime has this property. Okay, and also in terms of the group theory and covering spaces, we can similarly say that a group gamma is virtually, again, some property if there is a finite index subgroup let's call it H of gamma, so this is finite index, such that H is actually has this property, okay? So that's just what it means to have a virtual property. And it turns out that hyperbolic 3 manifolds have lots of very interesting and very nice virtual properties. So here are some examples of virtual properties of hyperbolic 3 manifolds. And again, this is going to be a hyperbolic 3 manifold of finite volume. So the first example is something that we now know is true, that M is virtually Haken. Okay, and what does it mean? Haken means that it virtually contains an embedded essential surface. So M itself might not contain any embedded essential surfaces, but there is some finite cover of it that will. So another virtual property that M has is that not only does it virtually contain an embedded surface, but M is virtually fibered. Over S1. So in particular, that means, let me say that this means that M is virtually homeomorphic to a mapping torus. And that means that we can realize it as sort of, you take a surface, we cross it times an interval, and then we glue the top to bottom along some homeomorphism. And this is what we call a mapping torus. We usually denote it something like this. So M itself might not be fibered in this way. It might not be a mapping torus, but there is some finite cover of it, which is. Okay, that's a great virtual property. Another great virtual property that's maybe more group theoretical is that M has virtually infinite first Betty number. And what that means is that, let me say that here, what it means when I say virtually infinite first Betty number, I mean that for every like large integer that you can think of, there exists a finite cover, let's say n prime of M, such that the first Betty number of this cover is greater than n. Okay, so it's basically just saying that you can make the first Betty number as large as you want in finite index covers. And one final property that I want to mention, and this is a property about the fundamental group gamma, is that gamma is large in the sense that it virtually surjects a non-abelian free group. And I'll tell you why I think this is a really nice property. So free groups have lots of covers. So if you have a group that virtually surjects a non-abelian free group, then your group has lots of covers, or lots of finite integer subgroups is what I meant to say. So your manifold has lots of covers. And we can use that sort of to count and to build lots of hyperbolic 3 manifolds as well. Okay. So it turns out that actually all of these nice virtual properties that I just mentioned, they follow from a stronger theorem, which is certainly a very famous theorem now. Sometimes I like to joke that this is a $3 million theorem, but this is the virtually special theorem. So this theorem is due to Agol, not joint, Agol and Weiss. So the results started coming out at around 2012, although Weiss just published a book on all of these virtually special theorems this year. I have not yet looked at his new book, but this book came out this year. So I'm going to say 2021 here, just for that reason. So what the virtually special theorem says is that if you let gamma be the fundamental group of a finite volume hyperbolic three-manifold, then gamma is virtually special. So again, this is another virtual property that is pretty strong, and it has a lot of consequences of these other virtual properties that I talked about before. So let me tell you what this special means. And special is a word that has many definitions in many different contexts, but in this case, this is special in the sense of Haglund and Weiss. And one way to think about it is, let me say it over here. So i.e. gamma virtually embeds as a quasi-convex subgroup in a right-angled Coxeter group. Okay. So if you don't know what quasi-convex means, you should think about it as like a particularly nice embedding. And a right-angled Coxeter group, let me just remind you what that means. It's just some group which has a presentation that looks like this. Let's say you have some number of generators, they all square to the identity. And also, if you take two of them, you raise them to Mij. This is the identity where Mij is going to be either 2 or infinity. And you should think of infinity as there's just no relation between them. Okay. So it's a group that has this presentation. It's called a right-angled Coxeter group. And we know that because if you take a Coxeter reflection group, a Coxeter reflection group has this type of presentation. Okay. Okay, so that's great. This is obviously a great theorem. So we know now a lot about this fundamental groups of finite volume hyperbolic three-manifolds. And we know that virtually they have all these very nice properties. But this leads to a very natural question. So I'll say this here. And this is the question that we can ask. So now if we are given a hyperbolic three-manifold, M, which is virtually, let's say, some property we want, how do you find an explicit cover that realizes this property that you want? How do we find an explicit finite cover of M, which itself has this property that we want? Okay, and I will make a note here that the Abel and Weiss theorems are, even though they're great theorem, that they only really tell us about this existence of this virtual properties, but they're not effective. They don't really provide us with any indication that there should be an algorithm or a general algorithm that would allow us to find all these particular covers with the properties that we want. Okay. So, so it's unclear whether this is a question that could be answered in general, or if there could potentially be an algorithm that does this or not. However, I think a big part of my research has to do with trying to answer some of these questions for specific classes of manifolds. And in particular, a class of manifolds that I really like to think about are called arithmetic hyperbolic three-manifolds. So let me talk about those. And actually, this is a class of arithmetic hyperbolic three-manifolds and arithmetic hyperbolic three-manifold groups that I'll tell you how to construct them. And these are what are called arithmetic groups of simplest type. okay? And we can also refer to these, or these really come from groups of units of quadratic forms, and I'll tell you how to construct them, and you'll see why these are so nice. Okay. So recall from before that I mentioned that the isometry group of H3, we can realize it as this matrix group with real coefficients. So i.e. these are 4x4 matrices which preserve this one. So it preserves this quadratic form. So this comes from the quadratic form x1 squared plus x2 squared plus x3 squared minus x4 squared. Okay. So this this form is defined over the rationals. So we can say that this is defined over the rationals, and it has signature 3, 1. And here I'm just denoting and just making note of the fact that there's 3 positive eigenvalues and 1 negative. As you can see in this matrix of this corresponding matrix for this quadratic form. But we could have taken some other form. We could have taken any other quadratic form over some other number field, over some real number field, and seeing that this is actually isomorphic. So let me say it like this, to the matrix group that preserves this other form F with real coefficients if F is any, let's say, signature 3, 1 quadratic form over a real number field. Okay. So this is what we're going to do actually to construct these arithmetic groups. So if F is such a form, and for the purpose of this talk, I'm going to restrict to the fact to it being over the rational. So now I have a form with rational coefficients that again has signature 3, 1, which again just means that its corresponding matrix has 3 positive eigenvalues and 1 negative one. Then, well, I know that SOFs are, I can realize it as isometries of H3. But if I look at the matrices that preserve this form and just restrict to the ones that have integer coefficients, so it turns out that if I just restrict to these ones, this is going to be a discrete subgroup of the isometry group. So in fact, let me call this, let's say, gamma of F, because it depends on F. So then actually what I get if I look at the quotient of H3 by this particular group, which I'm calling gamma F, so this is going to be a finite volume hyperbolic 3-orbifold. Okay, so this might have some torsion in there, which is why it may not be a manifold, but it's an orbifold, and we can always actually very easily, we know how to do this, find a finite index subgroup of it, which is going to be torsion free. So that's going to correspond to a finite volume hyperbolic 3 manifold. Okay, great. So this, I've just shown you a very quick way that you can use these quadratic forms to actually construct finite volume hyperbolic 3 manifolds, which is great. And these are the 3 manifolds that we called arithmetic hyperbolic 3 manifolds. And the simplest types just really corresponds to coming from these quadratic forms. Okay, so but why should you care about any of these particular hyperbolic 3 manifolds that we construct in this way? And here is some example. So here's an example. If you take, let me draw this picture. So this is, here we go. So you might know this is the figure 8 knot. The figure 8 knot was one of the first knots that we knew that if you take S3 and you remove a neighborhood of the figure 8 knot, this is a manifold which admits a hyperbolic structure. So this is hyperbolic, and actually we can in fact realize it as this arithmetic hyperbolic 3 manifold of simplest type. So let me say this here is arithmetic of simplest type. So if you like knot theory, then I would say that your favorite knot should be the figure 8 knot, and if it's not, then you don't have the best knot. But the figure 8 knot is a great knot, and it's hyperbolic. It's one of the first known examples of hyperbolic 3 manifolds. It was studied by Robert Riley and later by Thurston, and sort of the study of the figure 8 knot really led to a lot of Thurston's developments. So it's great, and it happens to be arithmetic of simplest type, so we can realize it in this way coming from quadratic forms. Okay. So another, something that's really great also about quadratic forms is that they come with this particularly nice.
Ask a question.
Yes.
Yeah. So there's a quotient manifold. Are they could they be both compact or not compact?
Yes, that's right. So actually, I can say something really quick here. So these come from the quadratic form F. The quotient manifold is going to be compact if and only if this form is anisotropic. So as a quadratic form is isotropic if it has non-trivial solutions, and it's anisotropic otherwise. So if it has non-trivial solutions, that's actually going to build you some parabolic elements in your group. So the form is isotropic, then the quotient 3 manifold is going to be cuffed but finite volume. And if it's anisotropic, then the quotient 3 manifold is going to be closed.
You consider the form is diagonal. It's 3, 5, 7 minus 1. Is this it? This is what? Type 3, 1. Let's say consider the form. The diagonal is 3, 5, 7 minus 1. Is this?
Oh, is this form isotropic or anisotropic? I don't know how to tell immediately, but it is something that's fairly easy to check. Okay. Yeah. And also, I'm pretty sure this is something that you can just like plug into Magma, and Magma will tell you if it's isotropic or anisotropic fairly easily. Okay. Yeah. All right. So so that's that. So I was saying that these arithmetic hyperbolic manifolds, or I guess these groups, these fundamental groups, they come with a particularly nice family of subgroups that are called the congruent subgroups. So let me tell you what these are. If you remember, we had this gamma, let's say gamma F, which is this group SOF with integer coefficients. So in particular, this group is contained in the matrix group SL4, GL4C with integer coefficients. So we can look at reduction modulo n of each of the coefficients. So look at this, reduction mod n. And this lands inside of SL4 C mod NC, which we know is a finite group. Okay, let's say that this, actually, let's give this reduction a name. Let's say pi n. So then if we do this, it turns out that the kernel of this reduction, what this gives us is a group that we call usually like this. So this is a finite index subgroup of gamma f, as you can see. And I guess it's a finite index normal subgroup, since it's the kernel, normal subgroup of this. And you can see that we can do this for really any n. And again, if we were doing over some larger number fields, you could still do this because these are always integers. So this family, so this group gamma n is what we call the principal congruent subgroup of gamma f of level n. Okay. Okay. So now that I've told you how to construct this very natural family of subgroups, now I can state a theorem. And this is the theorem that I'll say. And again, remember that where I was going with was the question of if you're giving a hyperbolic three-manifold that you know virtually has some property, how do you construct a cover of it explicitly that has this property that you want? So we can answer this now, at least for these particular manifolds. So this is the theorem. And let's say given gamma f with f defined over the rationals as above, then actually I was able to show that if you look at the congruent subgroup of level 2, this is special, again, in the sense of Haglund and Weiss, and surjects a free group. Let's say surjects F2. Okay. And as a corollary, let me say here, this is a corollary. This also tells you that gamma 2 is actually itself Haken. Okay. And what I mean really by Haken is actually the quotient of H3 by this group. It's a hyperbolic three-manifold, and that's Haken. Okay. Any questions about this? Okay, so I'll just say also that principal congruent subgroups have been studied for a long time. They have lots of really nice properties. And because we can realize them as these kernels of these reduction maps, we can understand lots of things about them. For example, we can understand the index of these subgroups. We can understand things like their volume, understand things like their injectivity radius, and a lot more for these families of principal congruent subgroups. And the other thing that you should note is that in some sense 2 is sort of the best that we can do, because if you look at these congruent subgroups, other numbers are larger than 2, so 2 is pretty good. So I'll just say that. Okay. So let me know if you have any other questions, and otherwise I'm going to move on to a slightly different topic, but still related to these virtual properties. So, all right, let me do that.
So Michelle, I have just a quick question. So,
yeah,
did people consider also branch coverings, or just coverings that are really coverings?
These are really coverings.
Okay.
Yeah.
Okay.
Yeah. All right. Okay. So I talked about a couple of the virtual properties that I had mentioned earlier. Another one that I mentioned was the virtually infinite first Betti number. So again, let me just remind you what the first Betti number is. So if you look at the first homology of the three-manifold M with integer coefficients, then you get some number of copies of the integers plus some torsion subgroup. So this is a finite abelian group. So again, this is what we call the first Betti number. And the torsion subgroup is some finite abelian group. Okay. And so as I said before, virtually special, one of the consequences of the virtually special theorem, so virtually special theorem, is that hyperbolic three-manifolds have virtually infinite first-Betty numbers. So again, that just means that for any large number that you want, you can always find a finite index cover that has a first-Betty number that is as large as you want. Okay. So this gives us sort of a lot of understanding about first homology, at least in covers, at least in terms of this free part or free abelian part of the first homology, but it doesn't tell us that much about torsion. So we actually know even more about that. So we know that first Betty number can grow as large as we want, but there is also some control. And this, I'll say, is Luke's approximation theorem. Or actually, this is a particular case of Luke's approximation theorem. This theorem is a lot more general, but in the case of, let's say, hyperbolic three-manifolds, or even a little more general than that, you can take any compactly reducible three-manifold that's not a graph manifold. If you have some tower, let's say this here, this is any cofinal tower of regular finite covers of M, then if you look at the limit as I goes to infinity of the first Betty number of Mi with respect to the degree of the cover, then actually this limit goes to 0. So in particular, what this is saying is, well, you might have this cover, this tower of covers where you know that your first Betty number is growing to infinity, but the growth is very slow with respect to the degree, okay? So it gives us a lot of control on how fast the Betty numbers can grow, and in particular, they grow very slowly with respect to degree. So again, this tells us a lot about the free abelian part of homology, at least in this towers of covers, but it doesn't tell us that much about torsion. And unfortunately, we don't have any type of theorem like this with regards to torsion, but there is actually a conjecture. So this is a conjecture. And this is a conjecture that has been stated in a few different ways and for some more general cases. So there's some versions due to Berger and Venkatesh, as well as some versions due to Luke himself and to Tangle. And in this particular case, I'm going to say that there exists a cofinal tower of regular covers such that now we can again look at the limit as I goes to infinity, but in this case, I'm going to look at log of the size of the torsion subgroup. Again, with respect to the degree of the cover. And this number should go to volume of M over 6 pi. Okay. So again, this is just a conjecture. We don't know this, even though we understand what happens for the first Betty number, we don't fully understand what's going on with how torsion grows in terms of these towers of covers. But at least there is a conjecture that it should go to volume of N over 6 pi. And maybe I should have said here that here I want to take M to be a compact three-manifold. and I'm going to allow either empty or toroidal boundary. But I'm going to say that there should be at least one hyperbolic piece in its geometric decomposition. Okay, and if I do this, then when I say volume, this is really the simplicial volume, and you should think about it as you add up the volumes of the hyperbolic pieces, and if you have a piece that's non-hyperbolic, you say it has volume 0. So it should look like this. Okay. And actually, Le proves that he proved this inequality, that this is always less than or equal to, but it doesn't actually prove the theorem in general, or the conjecture in general. But again, this is just a conjecture, and it's probably really hard. So maybe we should ask actually an even easier question. So easier question. And the easier question is, can we even find a cover of M? Oh, let me say a cover, let's say M prime of M, where the torsion subgroup is non-trivial. So I'm not even asking like what happens in towers of covers or how does torsion grow, but can you even virtually find non-trivial torsion? So that's certainly a much easier question, and there has been some progress in this question. So let me say that the answer is that yes, this is true. You can at least find non-trivial torsion in finite index covers. The first result of this type is due to Hongbin Sun. So this is a paper from 2015, so it's fairly recent. And he showed that this is true in the case of closed hyperbolic 3 manifolds. So in the case of closed hyperbolic 3 manifolds, it actually does make use of the virtually special theorems, but it allows you to construct or to say that there exists a cover of any closed hyperbolic 3 manifold where you can find torsion in the first homology, and in fact, torsion as large as you want. And let me also say that there were some results that were, well, there's 2 results that were posted on arXiv independently, but within a week of each other, actually, that there's a result of Iliu as well as a result of Friedel and Herman that did something more general. So let's say more general. Okay. All right. So in the last few minutes, I just want to state another theorem. So this is a theorem which is joint with Daniel Groves. And in this theorem, I'm going to let M be a compact irreducible three manifold with empty or toroidal boundary. And with at least one hyperbolic piece in its geometric decomposition. Okay. And if I'm going to also let A be any finite abelian group, then there exists a cover, a finite index cover, or finite degree cover, such that A is a direct summand in the homology of this cover. Okay, so this is what I refer to as actually having prescribed virtual torsion in homology. So not only am I saying that I can find virtual torsion in a cover, sorry, that I can find torsion in a finite index or finite degree cover, but I can prescribe it. I can make it look like any finite abelian group that I want. All right, so I'm going to end here.
Thank you for the talk. So are there any questions for Michelle?
Could I ask a quick question?
Yeah.
So so in that last term, is it one of those kind of effective things, or is it not constructive? Where you just say that cover exists, but
yeah, unfortunately, this one is not effective. It's not constructive. It does use the virtually special theorems, which, like I mentioned earlier, are in their current form not effective.
thank you.
Any other questions? Okay, so I have some questions. So you have this Looks approximation theorem, you know. So the Beatty number, the first Beatty number divided by the degree of the covering goes to 0. Is there any conjecture about the asymptotic of B1, the first Beatty number, in terms of degree?
Perhaps. So I think when Luke studied this, a lot of it has to do with L2 invariance. And I think he also has some other conjectures, but I don't know them myself.
Okay, so for your result about this congruent subgroup, so you only need to go to gamma 2.
Yeah.
Is this term more generally for the, so you consider this arithmetic group of a simplest type?
Yeah, so this is not for general arithmetic groups of simplest types, but ones with forms that are defined over the rationals. So unfortunately, I think my arguments don't really work for other number fields. And part of the reason why is because for these arguments, I want to find these special covers. And like I said before, special, this really corresponds to being particularly nice subgroup of a right-angled right-angled Coxeter group. And in this case, what I do is use the fact that there is a nice family, like I guess a nice set of examples of right-angled Coxeter groups that you can construct from the standard quadratic form of signature 6-1. So this result sort of comes from like embedding these, I guess, embedding integral lattices of this lower dimension into this bigger dimensional ones. And it only works for this over the rationals because this bigger dimensional one is a rational lattice. So I do think there is maybe a possibility that one can try to show this more generally, but I don't know how to do that.
Is it known that there cannot be true in general? Is there no proof?
It's not known. Something that is known, something that was known actually even before the full generality of the virtually special theorems is Bergeron, Hagun, and Weiss did say that if you had something that's arithmetic of simplest type, you should be able to find a special cover that's a congruent subgroup, but that again doesn't really tell you anything about the level of the congruent subgroup. It's not known whether it can be, there can be a bound or some, it's not known.
Are there other questions? Okay, let's thank Michelle again for the very nice talk.
Ciao.
Thank you very much, Michelle.
Thanks.
Yeah, kind of surprising. You don't need to go to Gamma 2.
Yeah, it's nice.
Yeah. So.
Yeah, it's nice. I think it was, it's a little surprising for me as well.
Yeah, the last bit is also very strong. I think any finite Binning group you can arise as the direct sum in H1.
Yeah, so that's right. It's pretty nice. Actually, Honding's twin result was like this too. So it was also this prescribed torsion, but it only worked in the closed case. And the reason Hongbing's result only worked in the closed case is because he used Kahn-Markovitch to construct this. And you probably know Kahn-Markovitch, like this, lots of immersed hyperbolic surfaces only works in the closed case. But recently, a few years ago, there was a kind of generalization by Kahn and Wright, and that's what we use in our theorem. Yeah. Anyways, thank you. Thank you so much for having me.
Okay. What's your teaching? What's your teaching this semester? Is the 2-1?
What?
What are you teaching this semester?
So this semester I'm teaching 2 sections of like an intro to proofs class.
Oh, 2 sections. Okay.
Yeah.
For math majors or?
It's for math and computer science majors.
Oh, okay.
And I actually think maybe more than half of my students are actually computer science majors. But it's required for them too. Yeah.
Yeah, I want to thank you very much for the talk.
Yeah, thank you for the invitation.
Hopefully I can come here physically sometime.
Yeah. Yeah, hopefully we can start seeing people in person soon.
So is the seminar in your department in person or?
No,
mixed,
we actually are not having, or at least there's usually like a geometry and dynamics seminar, and we're just not having it right now.
Okay.
Yeah, so I don't know when it will restart.
How about the colloquium? Is it also?
I don't know. I think I heard that we might have colloquium this semester, but we haven't had any yet.
Oh, okay.
Yeah.
Keep us very careful.
Yeah. So yeah, I don't really know what's going on. And I think also this year, I know UIC is hiring, and they already decided that interviews are going to be virtual.
Oh, okay.
Yeah.
But we did have some conference already, mass conference, in-person conference.
I have some coming up next year in the summer. So actually my advisor's birthday conference is in June.
Oh, okay.
Yeah.
Yeah.
That's supposed to be in person in Austin.
Yeah, but hopefully it will be, okay by that time.
Yeah, we'll see. We'll see how it goes.
Just past July, no, July, end of June, beginning of July, they had this conference at OSU, in person.
Did you go?
Yeah, I went. Probably I'm the only one who wore the face mask. No, I mean, when I gave the talk.
Yeah, I heard about it. Actually, I heard from some people that told me they went in person, but I didn't. Yeah,
there's actually 2 conferences. They're consecutive. Most people don't wear face masks, but at the time, the level of infection is the lowest in the end of June, beginning of July. So it was okay. No one got infected. But that was.
Yeah, that's good. I think we'll probably get used to just wearing face masks forever.
A lot of people get the booster shot, so now it should be okay.
You got it?
I got the booster shot. Yes.
I see. I haven't. Well, I guess I haven't gotten my booster shot yet, but I think I'm probably gonna get one within the next month.
They have this. No, formally they have all kinds of requirements. You have to be of initially they're over 60 years old. They probably will lower the age limit.
Yeah, but I think here it's not. I think I'm eligible to get a booster shot now because it's been over 6 months for me, and I'm an educator, so it counts at least in Illinois.
Exactly. I think now it's okay. At the beginning, it's more strict. It had to be 60 years old.
Yeah.
Or you have some kind of high risk factor. I went there. I lied. I said I didn't ask me. They had to ask me to fill out a form. I said, okay, I'm a smoker. Yeah.
Yeah, because then you can go earlier. Yeah, but I think I'll probably try to get a booster, maybe around Thanksgiving or somewhere around there.
Yeah. Much safer.
Yeah.
Okay.
I guess I actually did go to something in person. I went to a women in geometry groups and dynamics in person in August, and I saw Tulia.
Oh, okay. She mentioned that. Right. Yeah. Okay.
Yeah, I saw Tulia there. And then the two of us had a complicated return because our flight got canceled.
Oh.
Yeah, because she was also flying to Chicago because she sometimes spends a lot of time in Chicago.
Right. She told me that I think her husband still has a house in Chicago.
Yeah,
I mean,
that's right. Yeah.
Also, meet with the friends over there, I guess. Yeah.
Mm-hmm.
Okay. Thank you very much.
Yeah, thank you.
Hopefully sometime can come physically.
Yeah.
Okay.
All right. Have a good night.